About a year ago, I made a video about hacking capacitive touch buttons. I outlined a really simple circuit that makes controlling a touch button from an I/O pin or any other logic level signal really easy. After I made the video, I was reading through the comments, and the general feeling that I got was even though this circuit is super duper simple and really solves the problem well, it still requires a level of hand soldering, assembly, building that most people are just not interested in doing. People really want a simple, modular, finished solution that makes this easy. Let's start by creating a basic list of specifications for this thing. 1. A small module that allows controlling products that employ capacitive sensing switches from an external logic signal. 2. It works with any self-capacitance type touch button, which is 90% of all appliance applications. 3. It's non-invasive. No disassembly or modification of the product is required. 4. It's totally isolated, safe to use on mains power devices with non-isolated power supplies. 5. It's inexpensive, $3 or less end user cost. 6. It installs easily with double face adhesive tape. 7. It's small enough so the modules can be stacked to address arrays of buttons. 8. It allows customization of the electrode size and shape to match the buttons on your specific appliance. 9. It has a simple 3-wire interface: power, ground, and trigger. 10. Electrical characteristics. A. Supply voltage and logic input voltage 2 to 5 volts DC. B. Almost zero standby power consumption for battery-powered applications. C. Low active power consumption. I made some simple design improvements to the original circuit. I cobbled together a little prototype so I could test it out on some real appliances. The circuit just takes a DC supply of 2 to 5 volts and a single logical input to trigger the capacitive switch. That's really all there is to it. So let's dig into this and try to really figure out how this all works. Fundamentally, we're just trying to emulate the change in capacitance that occurs when you move your finger over the button. When we place our new foil electrode over the capacitive sensor, we're fundamentally creating a new node in the circuit. There's a small fixed capacitance now that exists between the sensing electrode inside the product and our new electrode. Our new electrode has a small parasitic capacitance to the rest of the outside world. The sensing electrode inside the product now sees the capacitance between the sensing electrode and our new electrode in series with that electrode's parasitic capacitance to ground. If we now short our new electrode to ground, all we're left with is the inter-electrode capacitance between the internal sensing electrode and our new electrode. If the ratio between the parasitic capacitance and that interelectrode capacitance is high enough, the sensor will trigger. This is why we can't use long wires off of our new electrodes, because that will increase the parasitic capacitance to the point where it might not even work. The key to success here is two things. One is having a switch with the lowest possible parasitic capacitance. Number two is making sure that switch is mounted as close as possible to our new electrode to minimize the extra parasitic capacitance. So it's really more than just an electronic design problem. It's also a mechanical design problem too. We could totally get away with just using a reed relay to trigger the sensor. The only problem with that is the reed relays are big and expensive, and they also require quite a bit of power to drive, not to mention the extra circuitry you need to drive the coil. The average reed relay has a contact capacitance of around 1 picofarad. It's a pretty small capacitance, so that sets the bar for us in terms of electronic design. For our switch trigger device, I'm choosing to use silicon switching diodes as the switching device. They're super tiny, super dirt cheap, and they have actually a very low junction capacitance, somewhere around 0.5 picofarad, even better than the relay. Our circuit configuration is really simple. We have two diodes in series with our stimulus electrode connected to the middle junction. When these diodes are reverse biased, the only current that flows is an absolutely minute leakage current. So that electrode is basically just floating. The only thing it's going to experience is the minute junction capacitance of those two diodes. Now, if we reverse the situation and forward bias the diodes, they now conduct strongly, which basically looks like a short circuit as far as the capacitive currents are concerned. The only thing missing to make a practical circuit out of this is a resistor to limit the current flowing when the diodes are forward biased. All we need is like a milliamp or so. The currents that flow through these electrodes are vanishingly small, so as long as we're 1,000 times more current, it's going to work just fine. So let's consider what this looks like. With the diodes reverse biased, we basically have these two capacitors in series. But as far as the electrode is concerned, they're actually in parallel because both ends of them connect to an equivalent of a ground point. So if you add those two capacitors together, it's basically one capacitor to ground. And since these diodes are about 0.5 picofarad, the total capacitance is about 1 picofarad. It's just as good as the relay and so much easier. The next part of our design challenge is to figure out how do we create the bipolar drive signals to switch the diodes. If we use the input signal and feed it right into one end of the diode, we can see that a simple inverter will do the job. If the input is high, the output of the inverter will be low. That will create a forward bias condition. Conversely, if we make the input low, the output of the inverter would be high, and that will reverse bias the diodes. Now, the easiest way to create a single inverter is just to use a single open collector transistor. Using that with a pull-up resistor does the job. It makes the perfect signal inversion that biases the diodes exactly the way we want to. The circuit is drawn is totally complete, but let's add one little convenient element. We're going to add an indicator LED that turns on when there's power and the input signal is high. This makes troubleshooting so much easier because you can see what's going on at a glance. The only thing left to do is to figure out some part values for the components we've chosen. You see I've chosen 4.7K for the base resistor, the current limiting in the diode string, and the pull-up. The reason for this is because it's so not critical, it's so much more convenient to have a single resistor value rather than have three different ones. You could go blue in the face calculating the perfect resistor here, but it's really not going to matter. The circuit is so forgiving you could use just about any NPN switching transistor to do the inversion. The 680 ohm resistor is there to limit the LED current to around 5 milliamps at 5 volts. It drops off at lower voltages, but that's okay. The switching diode is important. We use a BAS316. At around -2 volts of reverse bias, it has 0.4 picofarads of junction capacitance. Pretty awesome. My initial thoughts around the mechanics for this thing or to make a simple 3D printed or injection molded plastic box that the PC board would just snap into. The PC board itself would have a little spring hanging off the bottom, which would reach down and make contact with the metal foil that we apply to the electrode. The flange at the base provides an easy surface to apply double-face tape, which will allow you to just stick this thing into position with a spring making contact underneath. It would be really cool if this little thing could be just a circuit board, but I don't think that's going to work for the following reason. I don't think you can get away with a one-size-fits-all electrode, because the electrode configurations on these products vary quite a bit. So that's why I'm using this self-adhesive copper foil so that you can customize it to the shape of your particular product. That's why this little plastic thing has a spring coming down which pokes and makes contact with the copper foil. It makes an interface between the two components there. The other thing that that plastic thing does is it lifts the board up off of the foil a bit so that the wiring that has to come up and meet this doesn't interfere with the electrode. The other concept that's important too is we need to be able to get in and manually activate these with your finger even with this device installed. I think it'd be really frustrating if you couldn't manually operate it with these things on there. It would drive you nuts. The other concept is, what kind of connector should we put on this? It needs to be scaled appropriately, not too big, not too small. Does it come in from the side, from the top? All very important considerations. So let's consider all this stuff and work this through. It's funny, even as I'm shooting this footage and talking about it, it just makes me realize how many little minute decisions go in to making something like this come together. And I'm really glad we're starting out with something very simple so that we can get going on this process without getting bogged down in something that's just too complicated as a starting point. So, join the conversation, hub.fernikes.com. Give me your design feedback, your likes, your hates, your intuitions. Let's together make this thing something that really hits the mark. As always, I hope you learned something and enjoyed this video. Please help keep this channel growing. Like and subscribe. Thank you very much.